You will need your laptops at some point, so you might as well take them out now. All right, so we talked about last week, we talked about light as a wave. You guys did the experiment, interference experiment. Today, we're going to do the opposite of all that, which is talk about light as a particle. And this is like the beginning of what we call modern physics. Before light was discovered to be a wave, Newton called it a particle and gave it a mass, gave light packets a mass, and used just classical physics on it. So there's forces that are acting on this mass, such as gravity. So if you were to shoot a light, eventually it would fall back down. Most of that was wrong, all right? So we're not going to consider what Newton talked about in terms of light. We're going to talk about what happened in modern physics with regards to light and particles and all that stuff. I have a couple of videos to show you guys at the beginning, which I think are pretty cool, but it needs for you to understand what a black body is. Now we're going to talk about black body radiation. A black body is an object that is so black that it reflects literally no light. Okay, so a perfect black body is you shine light on it and you don't see anything reflecting off of it, right? So right now my laptop is black, right? But you guys can see like the textures and some light reflection on it. It's not perfectly black, all right? And anything that you look at, the reason why you can tell there's a texture to it is because it's reflecting some light. I would say like 95% of the light is lost on that, but definitely not 100%, and definitely not close to 100%. So, knowing that, let's watch a couple of these videos. So we're going to talk about a material called Vantablack. And Vantablack is a nanotechnology creation that we have made, scientists have made, that's supposed to be the closest thing to perfect black that's humanly possible. All right. Again, sorry,
it is so black, it looks like a mistake.
My speakers don't work again. I don't know why. My speakers work, but the speakers don't work. So you guys are going to have to listen to my crappy speaker. All right, here we go.
It is so black, it looks like a mistake.
All these things might look black, and we might even call them black, but they're not actually true black. But this is closer to true black than anything else on the planet, and it's revolutionizing everything from space exploration to architecture.
It's very hard to comprehend the blackest black in the world. I mean, you hear it, it makes sense, you think you can conceptualize it, but seeing it is something very, very, very different.
So black that it changes the dimensionality of an object. It's not a colour, it's the absence of colour. So it's what happens when you have no light reflected back to the viewer. You see nothing, so your brain paints it as black.
It might look like paint, but it's actually made up of microscopic carbon nanotubes, which are grown in a lab just outside of London.
It's made from individual carbon nanotubes, and those carbon nanotubes are like very, very long blades of grass. And you imagine if you were a human walking around in grass 1,000 feet tall, how little light would get down to you. It's kind of like that, but on a very, very tiny scale.
It's pretty much like a black hole.
That's an interesting comparison, because this material is helping scientists peer deeper into the heavens than ever before. Acting a bit like a lens hood for a camera, Vantablack basically prevents lens flares in powerful telescopes. Reducing that stray light allows us to see some of the faintest and most distant objects in the universe. So the closer we get to achieving absolute black, the more we are able to explore the blackness above. But space isn't the only frontier. Artists, designers and musicians want to get their hands on Vantablack. Asif Khan is covering a building in Vantablack for the 2018 Olympics. when people look at this building, they will see a sort of a schism in space. It'll be like you're looking into the night sky. And in fact, we're creating a kind of star field within this blackness. So it will look like the Milky Way, but you'll be seeing it in broad daylight.
The ability of Vantablack is to really make us think more about the light that we have access to. It's got the ability to make us realise what a precious resource it is.
Just to give you a better perspective on things, I have a couple other videos. They're short. So let's go to the next one. What I want you guys to do in this video is try to see the circle when it's above the black square. Even when the camera is black, in fact, was it a circle or a sphere? A sphere, because when you look at it from the top and when you look at it from the side, it's still a circle. So it's actually a sphere. You see no texture on this whatsoever. A couple others. Apparently, this stuff is more expensive than diamond. Right now. Maybe later on it'll be more mass produced. So try to follow the laser pointer. See no reflection at all. All right, now what does this imply? That's the important part. Yes, this is cool, but really what does it imply? That's the important part. So here we have a person who's doing an experiment. This guy is just like a do-it-yourself kind of guy. He's not like a part of a lab or any institute that does research, but he does have access to some cool equipment that I find is quite interesting. I'm not going to show you the whole thing because it's quite long. I will show you the interesting part. I'll show you the introduction for sure.
Okay, today I'm going to be shining the world's brightest flashlight on the world's blackest black. So we're going to be seeing if we can get any light to reflect off of it at all, and we're going to be testing how hot it heats up due to the absorption of the visible light. Okay, so I have here a paint called Black 2.0, and this is touted as the world's blackest paint available on the market. So it's comparable to Vantablack if you've ever heard of it. And let me show you what it does to things. It's pretty amazing. So for example, here's a ping pong ball that I painted with Black 2.0. So it looks almost like a black hole. You can't see any of the curvature of the ball at all. It looks like it's a flat circle, when really it's a ball. You can even paint very shiny things with it, and it becomes like a black hole in it. So it's really fun paint to play with. You can make things like this, make yourself a black hole if you want. So Vantablack can absorb 99.965% of visible light. And Black 2.0 is similar to Vantablack, but I couldn't get any real value for how much light it absorbs. But it's the blackest black available on the market, so this is what I'm going to use today. So my experiment today is seeing if we can get a reflection using the brightest light shined against the blackest black. Will the dark elements coming into it. So if this color gets any lighter whatsoever, we'll be able to know that's a reflection on there. So now let's do 32,000 lumens. 3, 2, 1. So look, you can totally see the flashlight on there.
Brightness.
If this black 2.0 were really absorbing all of the light, you wouldn't be able to see a shadow on there at all. But you can totally see my hand shadow on it. So this means the 32,000 lumen flashlight overpowers the black 2.0. So now let's check how much the black 2.0 is heating up due to the flashlight on it. Okay, so before I shine the flashlight, it's about 20.1 degrees C, 20 degrees Celsius. So now we'll shine the flashlight on it and see what it jumps up to. Whoa, 24, 30, 33, 40, whoa, that's heating up fast. Look, you can just see the glowing red circle on there. So know that this flashlight is an LED flashlight and not an incandescent bulb. So it's putting out mostly just visible light, and the heat is coming from the black absorbing the visible light and turning it into infrared or heat. So it looks like it gets to around, it's going to about 55 degrees Celsius. Now let's compare that to what I do if I shine it on the white wall. So a white wall gets to around 30 degrees Celsius, but it definitely doesn't jump up as fast. So this material, Envanta Black, which absorbs 99.9% of visible light, can be modeled as almost a perfect black body. And a black body is something that absorbs all types of radiation. And now for the interesting part. If I were to ask you whether you think that this material or the sun is a better black body, so does this material or the sun absorb light easier?
I won't play the answer because I want us to talk about it a little bit. Well, what's important here is that it absorbed all that heat, right? So imagine you had LED. So that flashlight wasn't actually heating up that black body or the black 2.0 circle. It was actually just sending photons through it. And those photons were then converted to heat energy, which is crazy if you think about it, because all this energy is coming from it absorbing light. All right, and now you absorb this light, there's no reflection, that light transmission become one and two hours transmission become hot. You guys know that black cars absorb more heat in the summer. The reason for that is because they absorb because they're black and they reflect less light, so therefore they absorb more of the heat. This is that taken to the extreme. Now, the guy in the video said, is the sun a better black body or not compared to that black 2.0 or the black 2.0 or the black? It doesn't matter compared to that, but what you need to know is that the sun, does it reflect light or does it emit light? What is it? It emits light, right? So the light actually doesn't come towards the sun and get bounced off the us. It's a source of light. There are other sources of light. These are sources of light. And this is not a source of light. This is a reflector of light. And so is everything else. Right? Right now, you see me because there's light going from me to you, but I'm not emitting that light. I'm just reflecting that light that's being emitted by the light, or that's being emitted from the sun. Now, one phenomenon that I know that you guys might be familiar with is this idea that when you heat something up really, 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 really hot, what happens to it? It burns, but without it burning. A lot of times it's setting it on fire. I'm talking about just heating it up, making it really, really, really hot. Look at the picture I have there. What? It turns red or it glows rather. Okay? And that's the beginning step of understanding this whole quantum mechanics stuff is that things that are hot glow. Okay? The hotter it is, the glowier it is. How does it work? So this is hot, right? Would you say that this part is hotter or less hot than this part? So this is hotter or not as hot? This is not as hot. This is way hotter. What if it was super duper hot? What would it look like? It would be white. It would shift. The wavelengths would shift kind of. It would change color. And then you have different types of hot, right? Like you have like we're going to do this lab this week where you burn different substances and see the color, and based on the color, you're supposed to determine the temperature. But if you were to have like one of those lighters that lights up fire green or lights up fire blue, you guys ever seen those before? Or you throw a substance into the fire and the fire turns a different color. That is fire burning at different temperatures. The different temperatures will shift this wavelength, right? So far, that's all good. So a black body, what it does is it takes the energy and the energy from a photon, and it bounces it inside itself so many times that it ends up heating up. All right, and when it heats up, well, it starts to glow. All right, so the sun is that exact same phenomenon. It is such a great black body that it receives all of the energy from the universe, and then it made it so hot that it ignited into a big ball. All right, that's how the sun came up. In a perfect black body, no, it's absorbed as energy. That's it. No reflection whatsoever. Yeah, exponentially. Yeah, it would get infinitely hot if it was a perfect black body. There's no such thing as a perfect black body. So then, what scientists came up with, and imagine this is like the late 1900s, let's say the late 1800s, and so we have this idea, this what we call it ultraviolet catastrophe, and this is kind of scary if you think about it. So what they saw, they only saw this part of the spectrum, right? So I'll explain it to you. Here's the wavelength, and here's the intensity of of the, the light that's being emitted by a black body is heated up. If it's a low temperature, this is a red one, low temperature, you have a curve that looks like this. So there's a little bit of glowing, and the peak is about in the 600 nanometer. I cut off this part intentionally. And then you have, if you're really, really hot, if you increase the temperature from here to here, then it would start to glow green. And if you really increase the temperature, then it would glow blue. And if you really, really increase the temperature, it would glow white. As you, if you notice, these wavelengths are shifting towards the low small wavelength, right? So red's got the biggest wavelength, then green, then blue, and then so let's say we get all the colors beyond. What's on this side of the smaller wavelength than blue? Ultraviolet, right? So now we're moving into the ultraviolet category. So things are really, really, really hot, such as the sun, for example, then it would be only emitting ultraviolet. That's crazy, right? That's too much ultraviolet would all die of cancer. It's nuts, right? Or even just like a fire is really, really hot. So then does that mean that if we put something in a fire, all of a sudden we all over us? Well, that's what the ultraviolet was. And for a long time, there was no answer to that question because they couldn't see the other side. They figured the next hot one was going to go straight up and would be able to, this side of the spectrum would be too high. This side of the spectrum. So that's pretty scary. Well, then this guy, Max Planck, came along and he showed us the rest of the graph. And this is what it came up with. And while, yes, it does shift to the left, here the peak is at about 750. Here the peak is actually closer to 500 nanometers. The point is that the peak is shifting closer and closer to the left. But in the ultraviolet range, which is over here, it actually very quickly dies off. So yes, there's ultraviolet radiation, but very little other. So yes, the sun does emit ultraviolet and X-ray and gamma rays and all that stuff, but it just emits relatively very little. Most of it is going to be in the visible spectrum, right? And that shift is what's describing that change in color. So yes, blue, if it's so hot it's blue, that's hotter than if it's so hot it's red, but still not dangerous in the sense that it doesn't emit any UV. So this guy, Max Planck, is who came up with it, all right? So he answered the UV catastrophe, the ultraviolet catastrophe, and he described this relationship. This is the beginning of Einstein used this science to determine what was coming up next. He created an equation which we call the energy of a single photon. right? And so he postulated that light can be described as a single light packet, a single thing of energy. Nothing, no matter, no mass or anything like that, nothing like what Newton said, but just that it's a packet of energy, and its energy can be described by some constant and the frequency of that light. Okay? So the color of it basically, or the wave. The constant's written here for you guys to use later when you have to do experiments and calculations. Energy is measured in joules and frequency is measured in hertz. What you need to know is that this is the energy of one single photon. Okay, that's really important. If I were to ask you, let's say, for 10 photons, you would just multiply that number by 10. Okay, so far so good? All right, so that's what Max Planck contributed. Important, but not the biggest thing. So then this guy came along, and everyone knows him. It's Einstein, and he looks a lot like my dad. And actually, my dad has a brother who's got long white hair, like exactly like this haircut, but he's got a goatee, so I chose not to put his picture. Anyways, that was just for fun. Einstein actually came in and showed something. I was talking to my friend yesterday, because I was so fascinated in this world. I asked all my friends. One of them is a maxillofacial surgeon, so someone who does constructive surgeries on jaws. The other one is a pharmaceutical medical liaison, so he's a PhD in immunology and pharmacology. He kind of like works for many pharmaceutical companies in North America. Very smart guy. I asked my other friend who's who works for the government, very high position of the government. And I asked my wife, who's a family doctor, to name me 3 really famous scientists, right? I'm not going to ask you guys' name, but I'm just going to hear a few. Don't say Einstein, because his name is there. But just someone put up their hand and name me a famous scientist. Anyone? Newton, very famous. One other one? Good. Galileo, maybe one more, so we have 3. Who? Very true. Yeah, very famous scientist. All right. 3 scientists. I've asked you guys, I've asked my friends who are mostly also very smart people, some of which are in the medical field. No one was able to name me a single non-physicist famous scientist. Everyone is always able to name only physicists. Why? I don't exactly know why. Maybe it's just that's how pop culture came about. But can anyone tell me what Einstein did? The atom bomb? Yes, that's maybe not his most important. I mean, he improved on the atom bomb. E equals mc squared. Did he win the Nobel Prize? He did. For what? For what? In physics, but for what? What did he provide? So that's it. Tell me what you think of this. Relativity? Okay, no, that's a very common misconception. But that's what most people answer is the theory of relativity. What is Einstein famous for? Theory of relativity. That's not what he won a Nobel Prize for, and not his most important. Discovery. His most important discovery was giving birth to me. No, but the point is that the average person will name you Einstein as the most famous scientist, won't even know what he did, yet we have things as important as the vaccine, who we have no idea who invented it. So who invented the vaccine? Does anyone know the first vaccine? Does anyone know? Nope. Jenner. Edward Jenner. Does that ring a bell? No, it doesn't ring a bell. You know what? I had to look it up too. I didn't know who it was. And it's kind of strange how we only remember physicists, but we don't even know what they did. Yet all the more important discoveries, we don't know who did them. Not saying that physics is not important, because I'm a physicist, think it's important. But what about Einstein's relativity? If you guys think that's what he's famous for, what about relativity affects your life right now? Not so much. Really, really cool and groundbreaking in the world of science, but it's not affected by our in any case, that just had me thinking about it. Try to give love to some of those non-physics scientists because they're quite important. Those of you who are going to say Watson and Crick, who knows Watson and Crick? You guys know who Watson and Crick is? That's it, just one person? You heard of him? He discovered that in DNA, the A's bind to T's and the C's bind to G's. Watson and Crick base pairs. I don't know if you've heard of that. Those guys are also physicists, not biologists. Yeah. All right. So let's talk a little bit about what Einstein did, and this is where it gets a bit trippy. So he gave birth to what we call modern physics, and he also gave birth to what we call quantum physics, which is part of modern physics. It's an umbrella of modern physics. This brings us to the early 20th century, so beginning of the 1900s. Quantum physics, I'll just explain more modern physics, is really, 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 really good at explaining things that are either very small or very fast. Okay? Newtonian physics, or what we call classical physics, is what we use to describe like big objects that have a mass that are predictable and are in gravity and things like that. Okay? So like if I left an object here and I let go, most of the time it's going to fall down. Okay, most of the time, because you don't know. If I do that experiment a million times, maybe that 1,000,001st time is not going to fall down. Right? So I say most of the time it's true that gravity makes an object fall down. Einstein was famous for something called the photoelectric effect. Right? This is what he won the Nobel Prize for. And the photoelectric effect is the definitive or first definitive proof that light behaves as a particle. Okay? So imagine you're in the 1920s and this is the discovery that come up. Your mind is blown, all right, by this, and it's so elegant. I'll ask you a question. The reason why I thought of the reason why I thought of to ask my friends which physicists or which scientists they thought were famous is because if you think about Newtonian physics or Newton's whatever he discovered, he didn't really do anything all that complicated. He's like, yeah, things fall and they accelerate, and the force is proportional to its mass. That's all so intuitive that the only reason why he's famous is because no person thought to ever describe it before. He just so happens to be the first one to have done it. And so is all these things that Einstein did. It's going to be so simple that it's the only reason why it's so important is because he's the first person to have done it. And when you guys go in to become scientists and later on, you'll discover the big things when you discover are going to be very simple things that are just important, fundamental. So if we were to believe that light behaves like a wave, there's two predictions. Amplitude of the wave is going to have more energy, right? So if you have a high amplitude wave versus a low amplitude wave, the high amplitude wave is going to be more energetic. And that, and this is going to be described in the experiment that we did, that when you shine a brighter light on something, it'll cause electrons to move really, really fast. Okay, so let's keep those two in mind, and that's if the wave theory is true. All right, so let's put the experiment together now. The experiment, we're going to do it diagrammatically. If my explanation is no good, I apologize. This guy explains it better than I do. All right, let's move on. The photoelectric effect is the idea that you use the energy from a photon to mobilize an electron. All right, so the experiment is very simple. You have a sheet of metal, right? And the sheet of metal is made up of atoms that are ionizable. You guys know what ionizing means? It can easily become an ion. Okay? And most metals become a positively charged ion or a negatively charged ion. What? Yeah, most metals become positively charged ions, very easily become positively charged ions. So that means that they easily lose electrons. Okay? So what Einstein did is he shined a light, and the symbol for light in this case is going to be this kind of a funny V, right? It's kind of like, maybe I can do it better. I don't know. Let's just call it a V, and that's what light is. And it shines light on a metal, and what happens is the electrons on the top of the metal escape. Okay, shines more light, another electron escapes. right? So the prediction that I talked to you about in the last slide here, I said if the amplitude of the energy wave will release electrons better, right? And electrons will move faster when there's more intensity. So if I were to say this, if I were to shine whatever frequency, let's say green light, onto this metallic surface, if I had really bright light of the same wavelength, so let's say it's green, but I just made it much brighter, right? Then I should have more electrons, right? And that would support waves. Light is a wave, right? So I'm going to let you guys do an experiment later, a virtual one later. I'm going to bring back E&M here for a second. So this is the device that Einstein used. He put two metal plates like this in a vacuum. All right, so that's why I put a big circle around it. It's in a vacuum so that nothing, no gas particles interfere with the electrons or anything like that. And what he did is he shined light here, right? And electrons started to move in that direction. Electrons started to move in that direction. Electrons started to move in that direction. And so what happens is you're going to create a voltage difference between these two plates because all the electrons went from one plate to the other plate, right? And if this becomes negatively charged now, and this becomes positively charged now, then I'm going to have a current that I can measure. And this is how he did it. Look how simple this was. This is all he did is he took this device that he made and he shined light on it and measured if there was a current being made or not. And he won the Nobel Prize for this. So anyways, electrons start moving from one side to the other, created a current. We still haven't proved or disproved wave, or we haven't disproved wave, and we haven't proved particle yet. Okay, this is just the beginning step. So what I want you guys to do is answer a few questions from. All right, I have these 4 questions. There is a PhET simulation similar to what we've done. I want you to play around with it. It's super easy to play around with, but I want you to try to answer these questions. Okay, go do that now. Take like 10 minutes. So you can play with the intensity of the light up here, and you can play with the wavelength of light. Might be a bit harder to All right, let's take a look at this together. Here we have our Einstein's experiment. He has the two plates in a glass tube that's vacuum filled, which means that there's actually nothing in there. And it's hooked up to a current meter. For now, you don't need to know why there's a battery. Your battery is set at 0 volts, so essentially it's like there is no battery there at all. But the reason why the battery is there is because you can increase it and suspend electrons in the middle, right? So you can shoot off an electron and it's going to go towards the other end. But if this battery is shooting electrons in the opposite direction, which is what batteries do, then you can create a potential such that the electron has nowhere to go, left or right. And that's what is called a stopping potential. So you will use that voltage to stop an electron midway, that would be the stopping potential of that electron. That's how we would measure, that's how Einstein measured the actual joules quantity of the energy. But right now, that's not what's important for today. All right, what we need to do is answer those 4 questions. So the first one is, what does intensity do? So here we are. I'm going to get out of this. So I'm going to increase the brightness a little bit. Right, and what you notice is that these are electrons, and the electrons start to move away from the plate that's being irradiated, right? And the electrons are moving to the opposite plate. There is a current that's being created because now you have electrons that are moving through this metal wire and coming back. And so this thing will theoretically go on forever. So here I have a bright light, right? And so it's, I see my electrons moving. Now, if I were to increase the light, what changed? Someone tell me. Anything? If I were to now increase the light all the way to the end, what do you notice that's different than when there was only a little bit of light? So let me go bring it back to the beginning. So what do you notice about the electrons leaving here? There's more electrons when I increase the intensity. More electrons, right? But that doesn't mean more energy yet. Right? Bear with me. What happens if I increase the frequency here? So it's not obvious yet. What did you say they're doing? Is it, what's slowing down? The electron or the amount of electrons popping off? Amounts of electrons popping off slows down? Not quite. It's actually the electron itself is slower. It takes longer for the electron to go from here to here. All right. So let me just decrease the wavelength. And see, look, some of these slower ones are still going, and now I have my higher frequency, lower wavelength. They're making their way across really, really fast. So what physical principle describes things that move fast versus slow? Kinetic energy. All right. So where these electrons are getting their energy from is not from the intensity, but from the frequency. So far, everyone's following? All right. So these electrons are only fast because the frequency is making them go fast. So that means the energy comes from the frequency. All right. Now, if I didn't have enough energy, I'm just going to wait until those disappear. Do I have anything? I got nothing. What if I made it brighter? Do you think that's going to help? Full brightness, still not enough energy. If I wait, do you think it's going to happen eventually? Do you think it absorbs the energy over time, and then once it's got enough energy, it might shoot off an electron? No. All right. So that means that it cannot behave like a wave. The amplitude of the wave has nothing to do with this. Right? The fact that I'm waiting longer means that it also has nothing to do with this, right? The fact that if I shine this on here for 24 hours straight, I'm still not going to get a single electron. And the reason for that is because it's not a wave, right? It can't be a wave. If there was a wave, then all that energy over time would accumulate, right? So imagine you have a water wave that's constantly hitting something. Eventually, you're going to get enough energy to create something, some kind of like that energy accumulates, and this is showing that the energy does not accumulate, so it can't behave like a wave. But we still don't know if it behaves like a particle or not. Essentially, wave theory has been kind of disproven. Though we had the proof before that it had to be a wave, this is just disproving it. All right, let's continue with what we're talking about. talking is super slow today. Okay. All right, so we figured out that the energy is with response to its frequency. So we're using now that Planck's equation there, where E is equal to h and the frequency of light. So this also can be written as hf. I mean, it's the same equation. F is frequency, and this symbol is frequency of light. For all intents and purposes, I'm just saying that they're the same thing. Just don't be worried if you see it. Who took organic chemistry here? You guys remember when you did bromination under UV conditions? Does that ring a bell? Huh? I've even asked your art teacher if you learned this. She said yes. So let's say you have some kind of nucleophile, such as, what's a good nucleophile? CH. Yeah. Is that one, two, three, four? This needs it. All right. So let's say you have this. Sorry, not Br, but OH. Let's say you have this and you add bromine to it under UV light. You remember this reaction? So then you brominate this bromine, goes and replaces this in some kind of SN2 reaction, and it becomes CH2 CHBr, so, and then plus water. Ring a bell? Okay, remember this symbol here? That is like the universal symbol of UV light when you're talking about organic chemistry. I just want to point out that V there is the frequency of the light that you use. You can't just use any frequency of light. It's the special frequency for this. Now, so we figured out that this energy is proportional to its frequency, yet it doesn't behave like a wave. So what really is a frequency if we're not talking about waves? So everyone's kind of messed up right now. Let's get deeper into this. You guys have heard of free radicals? Reactive oxygen species? No? So this concept here is very, very important in biology and in chemistry and also for your life. All right? What do you guys do when you go to the beach? Especially as someone like Matei, maybe? Or yeah, exactly. Or maybe like Charles Antoine. He looks pretty pale. He needs some sunscreen. Why does he need that? To protect against what? Against UV. Why is UV dangerous? Well, why is UV dangerous? Does anyone know? They're full of chemicals. They're full of free radicals. So what did UV do? What did UV do in this experiment? It shot off an electron, right? So let's say you have a compound, such as in this case I use chlorine, but it could be any compound, right? And you shine UV light on it, or a high energy light like UV on it, so X-ray or gamma ray. But when you go to the beach, X-ray is the most, UV is the most common dangerous light. You're gonna cause ionization or a free radical ionization of the organic molecules on your skin, right? So you're gonna have, let's say, a carbon molecule. So I'm just gonna write R CH3, all right? And this, actually, in fact, I'm not gonna write it as CH3 like that. I'm gonna write it like this, right? And then you're gonna get your UV irradiation, and that's going to break this, that's going to break this bond. And instead of ionizing it directly, it's going to break the bond and give each side one electron. So that means this is going to go break like that, and this is going to break like that. So what that means is you have R, CH, H. Is this C now going to be negatively charged? What do you need in chemistry to be negatively charged? How many electrons? This is Chem 2 now that I'm asking you guys about, or Chem 1 even. How many electrons do you need to be negatively charged? 1 over the octet? No, it's a little more than that. You need 2. So this carbon is not negatively charged, it's free radically charged. And this H here is also not negatively charged, it's free radically charged. And free radicals, what they do is they bind to DNA and cause what we call double-stranded breaks. That's what causes cancer. So this kind of molecule, any molecule that has a free radical, right, is dangerous for you. They're called reactive oxygen species, all right, because, well, most of the times it's not carbon, most of the time it's going to be oxygen. So those are very, very reactive, and they're unpredictably reactive. So when they bind to DNA, they cause mutations, and those mutations are what causes cancer, right? So you want to protect against this radicalization. What is something that, you know, Dr. Oz will recommend you to take in order to prevent this? Antioxidants, all right? Now, the science behind antioxidants is actually quite proven. It is beneficial. What antioxidants do is they absorb free radicals, right? An antioxidant, most of the time, has this kind of molecule in it. What molecule is that? That's benzene, right? And this is what we call an electron sink. All right, this is called an electron sink, like a lavabo. Right? And the reason for that is because this is so rich in electrons. Look how many electrons are in this ring, right? And the fact that they're cycling, so these electrons don't stay in the same spot all the time. They're always cycling around the benzene ring, right? And if you put another electron in there, it doesn't really matter because it's always in a state of transient transition. All right, so it basically eats up the free radical, and it doesn't allow your molecules to be damaging to your DNA. The antioxidants, yes, do help. Now, what Dr. Oz might not tell you is that your body produces antioxidants already, so you don't need to consume pomegranate juice to cure cancer or anything like that. That's not how it works. I thought I would put this in because it's a very strong application of why this science is quite important. Though we still haven't proved that light is a particle. So far, so good. Any questions? No. Right. So we have to do this work function. Now, this is the most important part. You guys noticed when we did the experiment that when it was really high intensity, or sorry, when it was really high wavelength or low frequency, when it was like red, if we put it all the way to the red side, there was not enough energy to make anything move. So that means there was a minimum energy required. Yes or no? Okay, so the minimum energy required is important. Therefore, an energy is equal to, energy is equal to his constant times the frequency, right? If there's a minimum energy required and h is a constant, then that means there's a minimum frequency required. So far, so good? So that the frequency has to have a certain minimum in order for it to work. So what is that minimum frequency? We call that the work function, all right? No, this is energy. We had a graph, and we shined some frequency, and we were looking at the amount of electrons being released, or the amount of energy being used to release electrons. In this beginning part, nothing happens, right? The frequency has to meet a minimum. And only at some point here will you get the increase in energy and increase in the movement of an electron. We can even call this kinetic energy because it's the movement of the electron, or the kinetic energy of an electron. If we move backwards here, and we find the intersect here, then we can describe this as a y is equal to mx plus b situation, right? So you know what I mean by that? Like a linear function. Does that ring a bell? This is like the most simple type of function. So hopefully you guys know what this is. In this case, the y-axis is kinetic energy. The kinetic energy depends on some frequency, and that's going to be the x-axis. And what's going to be in front of the x-axis, the slope of it is going to be Planck's constant, so hf. And now we have to figure out what this value is here. This value is what we call the work function, and it's designated by the symbol phi, right? And this is, I'm just going to name it here. It's called the work function, and is the minimum energy required to mobilize an electron. Okay, so minimum energy required to mobilize an electron. If that's the minimum energy required, then we have this beautiful equation here, which I'm going to rewrite, and we're just going to rearrange it somehow. I'm going to say that I'm going to send over this to this side such that it's going to be HF is equal to KE plus this. Okay. This is the energy given. So if I shine some light onto the plaque, right, I can describe how much energy that is based on its frequency. And then that energy does two things. First, it's got to meet the work function minimum. Okay, so once it meets that minimum, then that electron has some kinetic energy. It's got a very little kinetic energy. If I give it just enough energy, if I give it just exactly this amount, then it's going to have no kinetic energy at all, right? But if I give just over that amount, then I have what we call kinetic energy. And the more frequency I give it, the more kinetic energy it's going to get, right? And therefore, what that means is that that energy gets converted into the speed of the electron, and not the intensity. It's not giving it the speed of the electron. So intensity is not a part of it. So far, so good? It's kind of abstract so far because, again, I haven't proven anything. I just disproven wave. That's all I've done so far. And we know that wave is proven too. So we're at an impasse. Let's take a break. Come back in 10 minutes. All right. Any second. Yeah. The red is hard to see. I'm going to switch to yellow, I think. Yeah, let's do that. All right, let's figure out what's happening to those electrons. First thing we need to know is what unit of measure we're measuring all this in. Obviously, it's always going to be in joules, but it's not always going to be showing up as joules. Sometimes you'll see another unit called an electron volt. And an electron volt is a measure of what I talked to you guys about with that battery before, where you can measure the voltage required to stop the electron. That voltage is called the electron, it's called the stopping potential. But for one electron, that amount of energy is referred to as an electron volt, and it's equivalent to 1.6 times 10 to the negative 19 joules. That number look familiar to you? What number is that? What is it? Mass of an electron? No, not mass of an electron. What? The charge of an electron, yeah, exactly. So it's a charge of an electron, and it's not a charge in this case. It's the same number, but it's been manipulated to be an energy quantity. So that's one electron volt. Now, assuming we have a Bohr model of an atom. So Bohr model of an atom shows you that there's an N of 1, N of 2, N of 3, N of 4. And these are the different energy levels. Okay? You guys have seen this kind of representation of atomic, almost like, yeah, it's like the Bohr model when you have different circles around the nucleus of an atom. I'm just drawing part of it. Now you have an electron that's here, all right? And if you give that, or if you excite that electron, it can jump up an energy level, correct? Yes or no? Yes. Okay. So you can jump up this ladder, and the electron can go there. This is called excitation, all right? And N of 1, do you guys remember what the name of N of 1 is? There's a special name for it. Starts with a G, not a GIF. What do you all stand on? Ground, yeah. So this is what we call the ground state. So N of 1, we always refer to that as the ground state. So sometimes in a question, I'd be like, the electron is excited from ground state. You should know that that's an N of 1. Okay, so the electron is excited, and how much energy was required to do that? Well, that energy is going to be equal to some amount of electron volts. I'm going to make up this value for right now, but later on we'll see that there's actually a calculation for it. So I'm going to say that this is a big energy leap. So I'm going to call this 7 electron volts of energy required to make this. All right, and then if you wanted to jump even further, then this is going to be, I don't know, 3 electron volts, and this is going to be 2 electron volts. All right, so what amount of energy do I need to give this system in order to make the electron just go away for good? Based on my diagram, I need 12 electron volts, because after 12 electron volts, I am at the highest energy level. Anything beyond that is going to be converted to kinetic energy and allow my electron to just go away, to fly off. Okay? So in this case, my work function is equal to 12 electron volts. Okay? Now, that's not always going to be the case. 12 electron volts might be an energy that's not attainable, and I might not give, and I might not give enough energy to make it fly off. Let's say I gave this system, I have an electron that started off at ground state, and I only gave it 8 electron volts. What's going to happen to it? It's going to go to N of 2. What's going to happen with that excess energy? Move faster? Yes and no. It's not going to fly off, so it doesn't have any real kinetic energy. So kinetic energy is really only in this region over here, right? So I didn't even give it enough energy to leave the orbital shells, so it can't have any kinetic energy. It would be what? Emitted where? Emitted? Yes and no. So your answer is, I think your answer is good enough. So if I give this system 8 electron volts, then 7 electron volts were used to excite this electron, and there's 1 electron volt remaining, and that's going to be used to create some kind of light. Now, let's forget about that for now. After a certain amount of time, this electron that's at your N of 2, where am I here? That electron that's at an N of 2 is not going to want to be there. It's not stable where it is. It's actually going to what we call relax. And as it relaxes, it's going to fall back down here. How much energy is it going to release? 7. It's going to release 7 electron volts. If it releases 7 electron volts, right? Where does that energy look like? Is it going to be exhibited as heat, or it's going to be used for light, right? And this is called an emission, right? And that 7 electron volts, if you were to do the calculation of Planck's equation using his Planck's constant and the frequency, you can figure out what the wavelength of light is going to be. So remember that, I'm going to write it up here. C is equal to F times lambda, right? So the speed of light is equal to the frequency of light multiplied by its wavelength. So if I have F there, I can do C over lambda is equal to F. So I can rewrite this as H is equal to, sorry, the energy is equal to Hc over lambda. And if I solve, H is a constant and C is a constant, so I can solve for the wavelength and I can determine what color of light is being emitted when this electron is relaxed. Okay? Is there any in between N1 and N2? There is nothing between N1 and N2. This is the number one definitive proof that light exists as a particle. Right? The fact that the energy can only exist as very discrete values of n of 1, n of 2, n of 3, n of 4. There's no n1.5. This is what we call quantum mechanics or quantum chemistry or quantum physics. It all has to do with these multiples of integers. All right, that's what all quantum stuff is. And when you break things down to the smallest unit of anything, we always refer to that as a quantum size, right? And like that, if you break down a centimeter, you can break it down into millimeters, break down millimeters into nanometers, break down nanometers into femtometers or picometers or whatever. Eventually, you keep breaking it down, the smallest possible thing, that's when we start talking about quantum mechanics. Then it's just a matter of dots. And those single value of dots are what we call quanta. Okay? So we can figure out what the light is being emitted. So at this thing, if I were to shine light on it, it's going to absorb light. Let me backtrack. Let's say I have hydrogen. One hydrogen atom like that. And my hydrogen atom has a certain amount of electronic configurations. Electrons can be on specific shells. There really only exist electrons on this one at a stable ground state, but it's not the only state that exists. So if I'm shining light on it, right? Let's say I shine white light on this. Okay? White light is made up of which frequency? Or which wavelength? Is it just one? Many, right? Okay. So if I shine many wavelengths on this, and there's one specific wavelength that does this, right? Because remember, the energy is only dependent on wavelength. Everything else is a constant. So it's going to take that one energy to excite the electron. So if I were to shine white light on this, draw that right now. I'll do white light. And do white light shining on this, it's going to use one of the wavelengths to excite the electron. It's going to use one of the wavelengths to excite the electron. And so which light are you going to see on this side? Am I going to see the one that is absorbed, or am I going to see all the light minus the one that was absorbed? What do you think, William? Yeah, I'm going to see all this light that I gave it, all that light, none of it got absorbed. None of it was used to do this, to do the jumping up. So on this side, what I'm going to see is all the same light minus that one wavelength. So I'm just going to draw it like this with one of the lines missing, right? So note that 4 lines go in, 3 come out, right? So kind of it's not a real representation, but that's essentially what's happening. You have 4 lights going in, 3 coming out. What happened to that one wavelength that was used to excite the electron, and then later on, it's going to get relaxed, right? But not at the same moment. So what's going to happen is that electron is going to orbit, and at some point in its orbit, it's going to relax and it's going to emit that missing wavelength in a different direction. So this is what we call absorption. And this is what we call emission. Right? Emission. Okay. So again, I just want to reiterate that we have light that goes in. One of the wavelength is absorbed. That's what's called absorption. And so the rest of the light keeps going. And when it emits that one wavelength or that packet of energy that it took. It's using that energy to emit this forcibly the same wavelength that it was absorbed at. All right, and that is very specific to hydrogen. Because this jump here, I said it's 7 electron volts. I made that number up. But whatever it is, if it's hydrogen, always going to have that same jump. Now, how do we calculate what that jump is? So there is an equation for that, which is the Rydberg equation, right? So I'm going to go back 1 second. This is hydrogen, all right? What's the atomic number of hydrogen? 1. Okay, everyone should have said that at the same time. The atomic number for hydrogen is 1, right? And I was talking about going from an N of 1 to an N of 2. So far, so good, right? So N of 1 to N of 2, that's the energy level I want to figure out. I want to figure out how much energy is required. So I'm going to need to use those numbers. So if I would go to my equation here, I have R, which is a constant given to you here, called the Rydberg constant, 1.097 times 10 to the minus 7, 1 over meters, right? Multiplied by the atomic number squared, which is 1 squared. And the so the initial, I is the inner energy level. In this case, it's 1, right? Or, yeah, 1. And then minus the outer energy level, which is 2. So it's going from 1 to 2. If I were to plug all that number in, I'll get a wavelength. And with that wavelength, I can figure out what the energy jump is for that shell. So let's do an example real quick. So what is the wavelength of light emitted by a carbon atom when an electron of the 4th shell drops to the ground state? Okay, and how much energy is released? So I'm going to remind you what the equation is. It's going to be 1 over lambda is equal to R, which is the constant, times Z squared times 1 over the inner shell number squared minus 1 over the outer number squared. R is 1.097 times 10 to the 7. No, not so much. What's the atomic number of carbon, guys? 4 is not 4. Isn't 4 boron or something like that? Is that? 12 is the atomic mass. So it's still not the atomic number. 6, yes, 6. All right, so that took us a while. Those of you in organic chemistry, shame. Those of you not in organic chemistry, shame. It's carbon, for crying out loud. The second most abundant atom on our planet. Oh, right, 6 squared, you're right. So what number do you guys get? Times 10 to the minus 9? Okay, got it. So don't do the 1 on. What did you get for just 1 over? And so if I want to find the wavelength, I got to take the reciprocal, which is now 2.7 times 10 to the 9 meters, which is 207 nanometers. 270 nanometers, is that in the visible spectrum of light? It's just outside the visible spectrum of light. It's pretty close to UV level. All right, so it's either violet or ultraviolet at that point. Now the point is, if you shine white light on a carbon atom, right, with 270 nanometers, right? Sorry, if you shine white light on a carbon atom, it'll absorb the 270 nanometer wavelength, right? So on the other side, you'll see all the colors except 270 nanometers. And then when it relaxes in the emission spectrum, it'll release only 270 nanometer light, right? And that is specific to carbon, right? There is nothing situational about this. Right? The only thing that determines this wavelength is which shells we're talking about within the carbon atom. All right, so that means that every single atom has a specific, what we call absorption, specific emission spectrum. So let's take a look at that. This is where things for me become super cool. So you've seen this hopefully on posters, right? And maybe you looked at it and you're like, what the heck is that? So here's how it works. This is a absorption spectrum, right? So this substance, whatever this substance might be, right, does not absorb all of these colors. All these colors are not absorbed. But where there are dark bands, they are absorbed. So you can figure out the wavelength of the colors that are absorbed by a specific substance, right? And you're going to have a matching emission spectrum. So an emission spectrum will kind of look like this, where you'll only have, everything will be dark, so it does not emit any white light except for those wavelengths that are previously absorbed. Okay? And that's specific to substances. So hydrogen has its own, helium has its own, lithium has its own, carbon, oxygen, nitrogen. And if something is made up of a lot of these atoms, then it'll have a combination of them all. So this is crazy because you can figure out now, based on just the light that something emits, how it glows, you can figure out what it's made of. Where is that useful? Okay? Planets, they don't really glow, but things in space that glow are stars, exactly. So understanding what stars are made of is super duper important. So here I have an example. So this is a continuous spectrum, so there is no absorption, right? And this is some unknown material that we don't know what it's made of, and it has this absorption spectrum looking like this. And here the emission spectrum of different atoms. So there's the emission spectrum of sodium, right? And you can see here that those two bands look like they overlap, right? And so maybe not this one, not this one, not this one, but this one is very, very characteristic of sodium. So you can say that this unknown substance has sodium in it, all right? And let's keep looking. This one looks like there's a band there, right? So it can either be hydrogen or calcium, so I have to do more analysis. But check it out, then there's a band here. So instead of looking at this as it could be either hydrogen or calcium, we said it's hydrogen because it's got the bands of hydrogen. There it is again, hydrogen. All right. So our unknown body, what we're looking at, has some hydrogen in it, has some sodium in it. We keep doing the analysis and we can make up exactly what it's made of. Okay? Again, just by looking at the light. That's it. You're not even touching the substance. You're looking at it, and you can tell what it's made of. Nuts. It's nuts. What is our sun made of? Here's that. Hydrogen mostly. How much percent? 70% hydrogen. That still leaves a big chunk. So what else is missing from that? The sun. If it's 70% hydrogen, 30% is going to be carbon. There's some very little carbon, not 30% though. It's helium. All right. And hydrogen's the first number. So will you write, William? Why don't you say it? Okay. Doesn't matter if you're not sure. Who cares? What's the worst that can happen? We all laugh at you. Ah. No. So our sun is made up of hydrogen, helium, and some carbon. So by looking at it, we can determine that. Now, how did that happen? How did our sun become to having that composition? And it's quite an important question. Before I talk about that, I wanted to show you this. These are the names of different stars, actual stars in space that we have named this way, and they're named based on their emission spectrum, or their absorption spectrum rather, right? Actually, sorry, those are not the names. The names are on the right. These are the names. All right. These are the names of the stars in some of the stars in the sky, and they each have their own spectrum. All the lines are different, right? And based on those lines, we can figure out what they're made of. Let's watch a quick video. I think it's pretty cool.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light, and each element gives off its own unique set of colours. So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac. And copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our Sun. And at first glance it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the Sun in the sky. But if you look a bit more closely, then you see that this spectrum is covered in black lines. These are called absorption lines. Each element within our Sun not only emits light of a certain colour, it also absorbs light of the same colour. By looking for these black lines in the Sun's light, we can simply read off a list of its constituent elements, like a barcode. For example, these two black lines, in the yellow bit of the spectrum, sodium, you can see iron. Right down here, you can see hydrogen. So by looking at these lines in precise detail, you can work out exactly what elements are present in the Sun. And it turns out that that's about 70% hydrogen, 28% helium, and 2% the rest. And you can do this not only for the Sun, but for any of the stars you can see in the sky, and you can measure exactly what they're made of. So that star there is Polaris, the pole star, and you can see that because all the other stars in the night sky appear to rotate around it. Now it's 430 light years away. But we know just by looking at the light that it has about the same heavy element abundance as our Sun. But it's got markedly less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our Sun. Whereas other stars are metal heavy. Sirius, the dog star, contains 3 times as much iron as the Sun. And Proxima Centauri is rich in magnesium. But although the quantities of the elements may vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth.
That means a lot. I don't want this. How do I stop? So we look at stars, and we know what they're made of, and we can use that information to determine how hot they are. Right? What a star is made of can tell us how hot they are. How do we know that? Why? Does anyone know why? How do we know how hot a temperature is based on which element? No one's making eye contact. Everyone just like, oh, he's asking us a question. So our sun's made up of hydrogen and mostly, and that's really after that it's going to be lithium, after that, and so on and so forth. The quantities decrease as the atomic mass increases. So if we're talking about the absolute number of atoms, they decrease with increasing atomic number. So the sun is so hot that it gives the atoms or molecules inside an incredible amount of kinetic energy. It's hot, so therefore more energy, therefore faster. So imagine now you have 2 hydrogen atoms, full speed because they got all this excess energy, and then they just collide. What's going to happen? What is that called? Okay? The hydrogen bomb. It's fusion. What do they fuse into? So I have 1 hydrogen atom, which has an atomic mass of what? 1. And then another one has an atomic mass of 1. And third one and the fourth one are 4 of these hydrogen atoms colliding. What is their now current atomic mass? 4. What has an atomic mass of 4? It's helium. Helium. Helium has an atomic mass of 4. So the temperature was so hot, it took a bunch of hydrogen atoms, smashed them together, made helium. And then what happens now? After it becomes really, really hot, what are you going to do with a helium atom? They're going to become something else. You're going to smash helium and hydrogen and maybe form lithium and beryllium and boron. And then you're going to smash them up and get carbon. And then all we have to build iron. Iron is, from what we can tell, the highest atomic mass atom that we can see in stars everywhere. In ours, is very small. But the more iron we see on stars, the hotter they are, right? Because they needed to have all of that kinetic energy, smash atoms together, so iron is big. Yeah. The ones that are hotter are bigger, right? I don't know if it's a chicken and egg thing. I don't know which comes first. Is it hot because it's big, or big because it's hot? No, I'm not sure. But they are bigger. The hotter ones are bigger, absolutely. And that begs the question, all right? There isn't a lot of carbon on our sun. We know that based on these spectral lines. And we are, as organic matter is, mostly made up of carbon. Where did that carbon come from? Did it come from our star? Our star, the sun, barely has any carbon. We got no carbon, basically. So we couldn't have come from our own solar system. I'm not saying we're aliens, because everyone's born here and things like that. But what you need to think about is that you're composed of many atoms, right? Especially many carbon atoms, even heavier ones. You have iron in your blood, for example, and you have even heavier ones, molybdenite and things like that. Gold, even there's some gold atoms inside you guys. The point is that these heavy atoms could not have come from our star. They came from other stars that were hotter, right? Because that's the only place where they can be made, is in hotter places. So if you think about it, this part is pretty trippy to me, is that no two atoms that compose you come from the same place, statistically, right? There are basically astral dust, space dust, right? And it just so happens that all of those atoms came from elsewhere in the universe and formed our planet, and we just recycle those atoms to form us, and then we'll decompose, but those atoms are still those atoms, right? And those atoms will decompose into the soil, maybe become fertilizer that'll feed a plant, and that plant will be eaten by an animal and give birth to another animal. So that carbon atom will do this whole kind of cycle or whatever and show up in something else. And the way it got into you is the same way. And eventually, if you trace it back, it had to have started on faraway stars, because our sun is not hot enough to have produced them, other than hydrogen. No, I canceled it. Back here. We got this, we got this, we got this. And so here's where the discovery and the definitive proof happened for the whole particle thing. And that was the whole point of this, is that what Einstein noted is that when he shone one photon, he got one electron. When he shined two photons, he got two electrons, three photons, three electrons. And you would never, ever get two photons, one electron, or one photon and two electrons, all right? Always been shine one photon, excite one electron. And so that means that light has to absolutely be considered to be a particle, right? Because if we're a wave, what do you consider to be one wave particle? That's not a possibility. A wave is an oscillation. It's a movement, right? It's not necessarily a thing. So thus was born the fact that light also behaved like a particle. You guys want to hear something crazy? I have another video, last video, and then we'll do some problems and then call it a day after that. So I have to admit, I will not pretend to understand this video, and I don't want you guys to understand this video as well. What I want you guys to do is understand what they're trying to say and how that might be trippy. And it's not supported scientifically yet. Although, so let me preface that. This is what was seen in a lab, right? But it is not described yet because no one really understands why that is, right? All right, so let's watch this.
Now, let's go quantum.
Sorry, it's the best explanation I have for this. It's called the quantum eraser effect.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. it behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave, but then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other we've had an influence on it which appears to travel backwards in time.
The experiment begins in the top left corner with the laser.
So you have this thing that predictably is going to produce a wave pattern, and then when you look at it, it produces a non-wave pattern, a particle pattern. And if you turned off the detector, it would behave like a wave again. Turn on the detector, it would behave like a particle, right? And there is, it happens after, like the decision happens dependent only on, like the guy said, that the experiment is conducted. So there is really like no real answer to this wave particle thing. And the current running hypothesis is that everything is a wave, including matter, right? So not just photons that we talked about in the light. We also talked about atoms behaving like a wave, and we talked obviously atoms behave like particles, but atoms also behave like waves, and light also behave like particles, and they always behave like waves. It's the current like biggest question mark in physics right now. The stuff that I'm talking about here was discovered in the late 1990s, so the early 2000s. This discovery was made, and that the work since then has kind of like evolved, but it's very, 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 very modern in its nature. Now, nuts, I find that totally bonkers. I can't get my head around it. All right. So here's what I want. I'm basically done. I want you guys to solve these problems. Once you've solved them, I'll let you go. Just show me that you're doing them. All right. Don't just pack your bags now and leave. All right. There aren't that many examples to do. There's one. There's two examples. There's not even that many. So do these two examples, and then we'll call it a day after that. Okay.